welcome back to UBC CS 532W, Grad, Prob Prog, UBC. I'm Frank, and we're going to talk about meta-learning today. Oh, this is a fun one. Okay, so last time we sort of finished like formal Prob Prog and we're now sort of starting to think about extensions to state-of-the-art connections to other fields, so on and so forth. But last time we covered, mixtures of reparameterizable and non-reparameterizable distributions and control flow, in other words, stochastic computation graphs. We explored the framework and could express those together. Using this formalism, we came up with an auto-diff-compatible deep probabilistic programming loss, which basically computes the right kind of gradients for you anyway. We talked about model learning in this context, right, and reparameterizing the model as well. So basically, at the end of the day, in some sense, like the deep Prob Prog part of the course is just about getting you to understand what this thing is, right, and what it means to learn a model, and what it means to learn an inference network, and why you would do this in an IID setting. So on and so forth. Now, I'm going to ask at the end for you to think about why and how what we're talking about today, which is going to seem much, much cooler than the stuff we've talked about in the rest of the course probably, why and how it's related to Prob Prog. And why, half of my group, payment included, has switched over to doing meta-learning, even though we're a Prob Prog group, right? So this is, and Jason, sorry, I don't mean to skip over you, Jason. You're obviously doing meta-learning at this point. So arguably, so too is Vasilios, and Ryan is going to be getting there right away as well. So everybody's kind of doing this, but the question is like, what's the tie to Prob Prog? And I want you to think about this in the back of your head as we're going through this. But just for something completely different, something to think about, let's consider a fascinating human capability, right? So the first time you ever saw a segue, and presumably you've seen segues before. If you haven't, the thing on the top is a segue, right? This thing. The first time you see one, you're able somehow to take that image or small set of images that you see when you glimpse it streaking by on the street and a name for it, and you're able to then classify other objects or images of other objects more or less immediately, right? This is pretty remarkable if you think about it, right? Because you have to have some sort of classifier in your head that takes an image and produces a class label, something like that, right? And we know that training such classifiers takes a relatively long time, right? It's we haven't talked about it in this course, but presumably we've done enough deep learning or regression modeling to know that that's not a straightforward thing to do. And it's very hard when you have a very small number of examples, right? In fact, you cannot just directly learn a classifier from a single example. It's like something that, it's not accessible to modern machine learning, generally speaking. So there's a lot of evidence that we can do this. I mean, it's obvious that we can do this, right? There's oh man, why am I? This is so embarrassing. I need to go. Yeah, Alison Gopnik at Berkeley does a bunch of child developmental psychology and has some very fascinating studies on basically how quickly children can learn new categories of objects. There's a fun story I could tell you about Tom Griffiths, who was one of her collaborators, his lab at Brown, blicket detectors. But basically, you say, this is a blicket, and then you have a bunch of other things, and you try to decide whether or not they're blickets, and people can figure out what a blicket is super, super fast. And they use all sorts of information from the environment and prior knowledge in order to figure out what a blicket is, right away. So if you're a deep learning aficionado, right, you know that one way to reuse past experience in order to like quickly learn a new problem is to basically do task adaptation, right? Or fine tuning. So you have some ImageNet classifier or something like that, and then you get some new data and you fine tune some final network weights or something like that in order to like quickly adapt to a new task, right? And there's some work in this area. Hierarchical models, in particular hierarchical nonparametric Bayesian models, are very interesting mathematical abstractions that allow for very, very fast learning of new object classes or new classifiers or so on and so forth. Think mixture models where you can infer the existence of a new mixture component very, very rapidly. But basically, in general, meta-learning is the name given to the subfield or activity that addresses this task adaptation process directly, effectively aiming to be as quick and efficient as possible, basically human-like. So there's some terminology in meta-learning that you're going to have to sort of adapt to really quickly, right? So in the standard supervised learning setting, models are trained on a training set, and their performance is evaluated on a test set. Because we're going to be evaluating our performance on new tasks or classification tasks or inference tasks or whatever, meta-learning requires thinking about sets of tasks or a set of tasks, right? And each task is going to be some sort of often supervised, but it won't necessarily be supervised, but there'll be some learning problem. I will think supervised learning, that's totally fine. In and of itself, and it consists of some context set, which is a small task-specific training set, for instance, the segue image, and a target set, which is a test set, or which is like this test set, or a set of vehicle images of which maybe segues are in that set. And a meta-learning model is trained on a set of tasks, which is known as a meta-training set, and tests on a set of new tasks known as a meta-test set. And the goal is to learn an appropriate inductive biases from the meta-training data set overall, and to exploit the learned inductive biases to quickly adapt to a new task. And this will become clear in just a little bit, certainly in the examples at the end. If we're talking about image classification, the number of classes in the context is called ways, and the number of examples per way is called shots. Okay, there are a bunch of approaches to meta-learning. So again, we've already touched on them just a little bit in the motivation. So there's an optimization-based approach, which is basically motivated by the neural network fine-tuning idea, where the adaptation step to some new task is done via fine-tuning some or all of the model's parameters. And meta-learning is basically done to learn hyperparameters of the fine-tuning step. So like basically some big gradient update, or like a central gradient plus some learning rate, learning steps, so on and so forth. And there are a bunch of methods within this class, MAML being sort of the, no pun intended, prototypical example. It's Chelsea Finn and Sergey Levin, those folks. There are metric-based approaches. So basically, if you can think of nearest neighbors algorithm, like as kind of an adaptation style thing, right? So basically, the meta-learning model in a metric-based approach learns some metric in which the items in the same class are close, right? So under this metric, they basically take new, they basically compute the distance of every new item in the target set to each item in the context set using this learned metric, which this metric can be adapted to the context set. And there's Siamese networks, prototypical networks, and matching networks, and Payman can fill us in on all the details of those. What we're going to talk about are the inference-based approaches, which are kind of a general framework that encompasses basically all of these things, but has a grounding in the kinds of approaches we've talked about, which is that inference-based models assume a unified generative model for all of the tasks, and meta-learning becomes equivalent to amortized inference, which is what we've been talking about for the last couple of weeks. The amortization step, so to speak, is equivalent to the meta-learning step. And fast inference at test time is basically equivalent to the adaptation step. And we're going to talk about this in detail. So, cool. So we have two different graphical models here. And they're cool and relatively simple. And you could write any of these in either a FOPL or a HOPL, but whatever. The more important thing is that you know how to do inference in these. So let's look first at A. So in figure A, we have a graphical model for a single meta-learning task. So this is some context set of input-output pairs. Okay. For example, these could be images and labels. Examples that we'll see earlier, these could be pixel locations and pixel values. These could be programs and their executions. These could be well, there's a whole bunch of things they could be. Let me give the other example from our, they could be rotations and images. You'll see what that looks like later. There is some unknown task-specific regression parameter that governs the output given the input. This is the target set, where the output given the target inputs is unknown. So this, in the case of image labeling, this would be an image, and this is its unknown class. This could be a rotation and an unknown view of an object in that, but from that particular perspective. Or it could be some set of pixel locations for which the values are not known. And there is some general parameter theta which governs this entire thing. Okay, and that'll be a little bit more clear what this is in example contexts. More to the point, this is a single meta-learning task, so you get a context, and you would like to do inference in a model, in this model, to get a posterior distribution over Z, and then use that posterior distribution to do posterior predictive inference over Y. Okay. Or you can think about this as just doing joint posterior inference over these two quantities with the goal of looking at the marginal distribution over the labels, which integrate over Z. Okay. Now, there's this model parameter, right? And this doesn't really make any sense in the Bernstein-von Mises sense that we've been talking about, unless we have multiple copies of something that we observe under this particular model parameter. So the meta-learning problem layered on top of this is to basically learn this parameter for whatever class of tasks we're looking at over the meta-learning training data set, whatever, where you have lots and lots of these tasks and labeled data for all of it. Doesn't have to be labeled for data for all of it, but usually you frame model learning as an EM or variational inference or whatever evidence maximization task, where the only latent variable is this Z, and you'd like to do Bernstein-von Mises on theta. Okay, so learn a point estimate on theta.
Can I just interject for a quick question?
Yeah, please.
With Bernstein-von Mises, you just mean you take some kind of maximum a posteriori type thing?
No, I mean we're gonna target this with a point we're specifically going to say that there are so many tasks that we can get a point estimate for theta.
Okay, sorry, maybe then that actually, like, I thought those were the same thing, a map and a point estimate. That's not, I should really know this.
No, this is fine. This is great. So if we, they're subtly different, right? So maximum likelihood implies no prior on theta.
Mm-hmm.
Right? Map implies a prior on theta, and both maximum likelihood and map are point estimates.
Yeah.
right?
Yeah, okay.
So if you go like this and you put some prior on this, then you could do inference over theta, or you could produce a maximum a posteriori, value for theta, which would be maximum a posterior under some prior, or you just do maximum likelihood where you say, screw the prior, screw regularization, we're just going to operate under the maximum likelihood principle, which in this particular case would be to maximize the evidence. Just remember that from our earlier conversations, Emma, maximize the evidence of this data, the observed stuff, which arises from integrating out the only latent variables in the setup, right? But if you remember the IID variational inference setting, this should look very, very much like one of these things because all of the latent variables are local. So we have basically an IID setup where we have local random variables, right? Okay, so fine. And I've already mentioned a couple of these, but it's important to sort of get your head wrapped around what we're doing, and then you can think about like, why is this Prob Prog? Obviously, this is something that one could use you could write such models inside of a probabilistic programming system, right? That's a straightforward thing to do and do inference in them. Totally cool, no issue, right? But there's also a use for them. Like there's a use case for meta learning in Prob Prog, and actually, again, why the group got into it. So we have Mr. Oh, that's de-anonymizing. I hope that's okay, Payman. We have Mr. Patani here. Where'd you go? He's not even here anymore. Okay. Who has worked on this application where we have a context set, which is a small number of labeled images for a number of novel object classes. XT, which is the input target, where are going to be test images to classify. YT are the target labels, which are unknown. And here it's like which of the context set classes are the new images. We have novel perspective re-rendering as an example application where the context set are images and angles of an object from various perspectives. The target inputs are the poses of the desired objects, or like the camera poses of desired perspectives, and Y would be the image of that object from that perspective. Image completion, we have a subset, the context is a subset of an image's pixel coordinates and colors. The target is the coordinates requiring colors, and then the value that the target inputs that are the pixel coordinates requiring colors. The target outputs are the colors of the target pixel coordinates. Program synthesis, we've got source code and observed program output. Then we have X or the XT are the observed program outputs, YT source code of the program that could generate the given outputs. Like there's a whole bunch of stuff that can be put in this framework. You can ask Jason about meta learning for auto ML, or you can ask Ryan about GPT-3 and why GPT-3 is a meta learning model. They're all it's all in this class. Okay, so we're going to do some notation. It's a favorite thing to do, right? So we're going to say a task is basically represented by a latent variable. That there's one latent variable Z per task, and the task consists of a data set of input-output pairs X, Y that are randomly split into two subsets called the context set and the target set, right? And again, these are analogous to a training set and analogous to a test set, and we want to be able to do very, very well in the test set super rapidly given the context set. So more formally, a task is defined as, cal C, cal T, where cal C is the set of input-output pairs for a context set, and cal T is a target set. And for any of the pairs, for any input-output pair, their relationship is governed by some likelihood function here, P of Y, given X, Z, and this global parameter theta, where Z is fixed for a task, right? And again, X might be an input image, Y might be a label, right? You can think of Z as being the parameters of a neural network if you want, right? Or in the case of Payman's work, local adjustments to the parameters of a neural network, where theta is the set of global parameters trained across all tasks for a classifier. Just to make things a little bit easier, we're going to define x cal d as the set of inputs and y cal d as the set of outputs in the tasks data set. Right? And we're going to say x cal c, y c, these are the context and target sets. Okay, so we have the full data set, which is x d, y d, and then we have the context and target sets, which are xc and yt. Context, target, full data set. Make sense? So far? Keep track? Okay, great. So the task, if we go back to the graphical model, is to learn theta and to do rapid amortized inference of the value of z for test time posterior predictive computation of target given target output given target input. Okay, that's basically what this says. So the goal of meta learning is to, one, given a set of training tasks, learn a model metaparameter theta, right? And then estimate the posterior predictive distribution as quickly as possible, which involves integrating over z. And z may be direct distributed as it was in Payman's work. So based on the graphical model, which again, just for, z, x, c, y, c, y, t, x, t. Whoa, hello. We know that the posterior predictive factorizes. In particular, this is, again, this is factorizing over task. This is just basically saying there is this huge plate here, right? So for this reason, we can focus on a per task posterior predictive. This is, in other words, there's a 1z per task, right? And that term, which just integrates over z, looks like so. This is the posterior predictive for a particular task. So this likelihood term here suggests that a task encoding is basically the parameters of a regressor classifier linking the target inputs to the target outputs. This is basically what I said before, right? So in other words, you can look at what's happening here as it's just the posterior predictive in this model. So we have the context here, you get the posterior predictive over z, and you integrate over z to produce the likelihood. But this particular form says there's a regression relationship between the input and the output, or a classification relationship, right? The unfortunate thing is that this term, right, is generally intractable, right? It's a posterior distribution like usual. So at test time, we usually replace this with some sort of parameterized distribution, which is going to be a variational approximation. So this framework that we're talking about, which you really can just focus on the graphical model that we were looking at, and you can derive everything from it, is encompasses basically most meta learning methods. So there's these methods differ on how theta is learned, and then how the posterior approximation qz given the context set and some parameter phi, which is which is going to be some variational parameters learned, and what overall model architectures are used. And we're going to look at two, I think. So we can see meta-learning as amortized variational inference by basically setting up the problem as a standard variational inference task. So we have a conditional distribution of the observed data, which again, I should go back to the graphical model. Sorry, we should just have this. We should just have this around. We're talking about this graphical model right here. So we have all the stuff over here. You have all the stuff over here. So we have all this data, and we would like to maximize the conditional evidence, right? And that involves integrating out over integrating the joint over Z, and this involves integrating over should we start over here? Let me try this again. The evidence for this graphical model involves integrating out all the Zs. All the Zs are local to particular data items, okay? Or to particular metadata sets. So there's an expectation over all the data, and then in order to integrate out Z, we either have to integrate out Z directly, or we can bound it in the same variational way we have before. And this is basically what's happening here, right? So hopefully this is clear. I could redo the derivation of this if I need to, but like it should be clear at this point to everyone what's going on here. Are there any questions about what's happening? Emma, are you wearing sunglasses? Questions about this or no? This should be clear. No questions? Clear? Adam, clear? Namrata, clear? Oh my goodness. Emin? Ish? Okay. Let's power on. Hopefully it will make sense. So if we, just like we've been talking about, if we maximize, we've talked about model learning and amortized inference, right? This is the elbow for the entire over all the data sets, which we can sample data sets from some labeled data source, right? So splitting training and test into context and not. The only latent variables are Z. We want to integrate those, integrate over those, but the things that we want to learn are theta and phi. So theta are the overall model parameters that we talked about, and this amortization artifact. Okay, fine. So maximizing the elbow with respect to phi learns the amortized inference artifact that we're after, right? optimizing with respect to theta learns a problem-specific generative model. Okay, and basically optimizing both, like we talked about, results in an amortized inference artifact for the overall problem domain. Okay. Let's do a specific instance of this, and then see if there are some questions that get generated, hopefully. So neural processes are deep neural network conditional generative models that are motivated by Gaussian processes. So they assume the same generating process that we showed in the graphical model, but they use a slightly different training objective. And they have specific architecture choices that correspond to the independencies that are implied by the graphical model in figure 2, the main graphical model. So yeah. So neural processes, if we go back to the to this expression, which not everybody is getting apparently, which is painful. If we go back to this expression, this is maximizing the model evidence in the overall graphical model. That's just what it is. And you can learn the model and the variational inference artifact in that model, and that's great for model learning. But in this particular case, it's not really what we want for amortized inference, because this is conditioning on the entire data set, XD and YD. Okay, so we haven't partitioned the data set here. We're just talking about doing amortized inference in the overall graphical model. Okay, let me go back again, and hopefully this will make sense. I'm terrified that there aren't questions or there isn't full comprehension. So let me just go back and try to make it happen. Okay, so what's the evidence in this model? Or what's the data?
What's that subscript?
So great, thank you for asking. Hopefully, I was hoping that would happen at some point, right? So So there is one big set of data. It's a little bit confusing. I'll give you that. Where did it go? There is one big set of data, right? So there's XD1, YD1, XD2, y, d2, so on and so forth. Okay, so these are fully labeled, fully everything data sets. And there's a bunch of them. Okay, so in other words, we have a context set and we have full labels for a target set. Okay. The likelihood of the full data set, and I like the data metadata set, which we haven't denoted, right? The full likelihood for the metadata set is this thing, where each of the individual things is marginalizes over its local latent variable zt. Okay, so in the way that we did IID, in the way that we did variational bounds for the evidence lower bounds for IID models, right? We know that if we want to compute log this or log this, then these break into the sums, right? And then we know that the log of, this guy, right, is greater than, and then we're off to the races. Okay, so that's all that's going on here. So we have some big data set, and we need to learn a few things. So one is we need to learn theta, which we can have some q phi for learning theta in this big graphical model. But we want to repurpose this q phi to be one that also works over here. And this is the subtle part about meta learning. Okay. Okay. So again, maybe this now makes a little bit more sense about what's going on here, right? So for notational convenience, we define xd as a set of inputs and yd as a set of outputs in a task data set, right? So this is some given data set, right? So we've got whether it's in the context or target set, right? And we split up xd and yd into context and target. But right now we're talking about fully labeled data, okay? Fine. So this doesn't, we could go through that, but it doesn't really matter. What matters is that on a per data set basis, right? This evidence, this log likelihood, this conditional likelihood, which again only has to integrate over z, is via Jensen's inequality and basically the standard elbow argument greater than or equal to this quantity, right? The expectation over Q, which is going to be our inference network, where here this inference network is using the entire data set, xd, yd, right? And we're integrating over just the latent variable z, okay? Fine, okay? So all this is basically saying is we're doing some kind of variational inference to do model learning. We need to learn this theta parameter given our huge metadata training set, okay? And the way we're going to do that is we're going to do gradient ascent on this elbow term, which is a lower bound on the actual evidence. So the higher we push this, the higher the evidence, which means the higher the model, which basically this is the objective for doing maximum likelihood on theta. Okay. And again, this is saying out of our huge meta learning data set, right? We integrate over all possible data sets. and compute this bound. Now, why the Bernstein-von Mises thing makes sense, if you think about what's happening, is basically we're going to construct this, and this is maybe even the most confusing part about the entire meta-learning thing. We're going to have some labeled data set and we're going to have a huge number of labeled images or whatever, input-output pairs. So the question is, what is D, right? D is a random sample of data items from this data set. So if this is a combinatorially large choice here, right? It's basically choose a subset of some size. You get to pick the size from the full data set. So there's like a gajillion of these, right? This is basically infinite. For all intents and purposes, infinite. Right?
Sorry, can I ask something?
Yep.
So why do we even split the data into context and target if we're going to be using the whole thing?
We're not. So that's exactly the, thank you. This is a thank you so much, Ina. I really appreciate it. Right? This is great. We're doing this right now to just talk about how to learn theta. Okay, just to set it up, say there is the overall variational objective, right? And if we wanted to do model learning in this, we have to do maximum likelihood. If we want to do maximum likelihood, we have to have some sort of inference network. We have to have some way to draw basically approximate posterior samples. And this is what we've been talking about this entire time. Amortized inference, variational inference, so on and so forth. Okay. So we construct this weird setup where we have the entire data set and we compute all of these terms. Okay, fine. So we can learn the model in this way, so we can learn theta in this way, but this particular variant of the inference network is not particularly useful, again, for exactly the reason you identified, Dina. Like we're conditioning on the full data set here. Okay.
Wait, Frank, before you move on, can I ask, I've been staring at equation 3 and 4 for a while, and I can't, you discussed this last week, but where does the expectation over a PD come from? Is it I thought that was from some other probability term that I don't think
it's not. So that's why it's a little bit difficult to to talk about this, right? So this t equals 1 to whatever thing here basically says that, there's a bunch of ways to set this up, but if you're in, for instance, in the image classification case, you're going to have a labeled data set. That's what you're going to start from, okay? You've got images and labels, right? And the way you make a task, like you set one of these, is you pick, in choose k. You choose k, where k is the size of c and the size of plus the size of t, right? So you choose k out of the n possible labeled things, and you make some of them a context set, and you make some of them a target set. Done. So this outer plate, which is the expectation over D, it's big. We could write this as choose one of the n choose k data sets. That's probably the most coherent way of saying it. But the overall setup is that you have some source of these meta learning data sets, and you have a distribution over them, and you want to perform inference in that distribution of data sets.
Or you're not even drawing from a finite set, but you're actually generating the examples, right?
Correct.
That makes total sense why you would include the PD.
Yeah, that's the point, right? So this is one of the inside this is basically the elbow for the inside, and this is just the expectation over the outside, right? Okay, so really this is basically, you know, amortized variational inference in an IID model. That's exactly what this is, right? Fine. To make this more interesting and more of a meta-learning style thing, neural processes are basically deep neural network conditional generative models, blah, 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 and they assume the same data generating process as figure 2, but employ a different training objective. And let's take a look at what it looks like. So for, again, a particular task, so one of the data sets, we can look at the thing that we, we can look at the joint distribution of yt, xt, z given the context and theta, and we can just write this down as the joint distribution specified by the graphical model. But we can break this joint distribution up in different ways. We can factorize it in different ways. So one way that we can factorize it is to factorize it this way, which is to say we look at the joint distribution of the target given the latent variable and the context times the distribution of the latent given the context. Okay, so this seems totally natural, right? But note that this is not the same thing. So like this would ordinarily be the product over, you know, this would ordinarily be the product over P of y, t, how do I index these? I forget. I given x, t, i. This joint distribution, according to the graphical model, would be z theta p z given theta times product over j of y c j given x c j z theta. So this is the factorization under the graphical model, right? Alternatively, we can just factorize this in this way, right? So we have the likelihood of the target data, right? Which I suppose we should just write this, just to be clear. This is equal to we have the joint distribution of the target data times the posterior distribution of z given the context set data. Okay. So what happens if we put this into the variational objective that we were looking at before, right? So the variational objective we were looking at before on a per term basis looked like this, and it looked like this. Right? So we basically factorized the joint distribution according to the graphical model. So this is the graphical model joint factorization. This is not the same as the neural process factorization, and it's important. So we're looking again at the elbow for a particular task, and within that task, we're looking at the conditional likelihood of the data, the target data given the given the target inputs and the context. So we of course can write this as, this is just the elbow. We're going to integrate over the latent variable. But here instead we use the factorization of the joint that we were just looking at. So yeah, that's all I can say. Except this would be a weird thing to do because this posterior distribution is intractable. It's something that we don't have access to, right? So it's a weird thing to consider doing. So in other words, this posterior distribution is intractable in most generative models, even certain, let alone deep generative models. So what neural processes suggest doing is kind of crazy, is to replace this posterior distribution with the variational distribution conditioned only on the context set. Basically, this is the sequential posterior update that I sort of started hinting at the beginning, right?
I have a question.
Awesome.
Yeah, that's like really confusing. So it's like the queue part of like the queue that contains the whole data. Like I don't know how do these two relate. They kind of seem to write the same but different. They even have the same. They have the exact like parameters. I don't know.
They have the same parameters. They have the same function signature, but they take different data. One takes the full data set. The other one takes some of the data set.
I understand that. I just don't see how it works. Like
fair.
Like how would the distribution look like? It kind of seems that the one is contained within the other, but maybe not really.
So the context set and the target set are distinct, right? So yeah, I will admit this bound is a little crazy making, right? It's confusing the first couple of times you see it, because it's not a bound anymore. It's just an objective, right? So this is like the last bit of craziness that we are going to like. This is max level of craziness that we're going to get to in the class in terms of like just manipulating these kind of variational bounds, right? We've done a lot. They're not going to throw reparameterization on top of this or anything like that. But the magic happens because basically this queue is basically solving the posterior inference problems in order to learn theta, right? But this queue and the fact that we're using the same for these two amounts of data has to learn how to produce an approximate posterior distribution that is correct for multiple amounts of conditioning data. And this is where the Prob Prog connection comes in, right? So basically, if you want to do amortized inference, when you have a varying amount of observations, you need to do something funny, right? You need your amortized inference artifact to have a function signature that takes a different amount of data, right? And that's exactly what's happening here, right? So the context set is distinct and generally speaking smaller than YD, but obviously, if Q is like under the variational objective, Q of Z given XD, YD, phi, that's targeted to be very, very close to P of XZ given XD, YD, phi, right? But if this objective is going to work, also Q of Z given C phi is going to be close to P of Z given C phi. And that means that Q has to learn how to generalize over different amounts of context data. Okay. So again, you can think of this as just D. This context target is just D. So we're going to like take an expectation over data sets. And we're going to have some amortized inference artifact Q, which again takes a variable size data set, either the size of the context set or the size of the target set or the size of the full data set or whatever. And we're going to compute per task bounds, variational inference style, try to maximize all of them simultaneously via stochastic gradient descent over all of these data sets. Right? By maximizing all of these bounds, with respect to theta, we're doing model learning over the space of all tasks. And when we maximize with respect to phi, we're going to be learning an amortized inference artifact that simultaneously targets at least 2 different amounts of conditioning data, either the full amount of data or the context. Right? The really fun thing is that generally speaking, when you construct these tasks, which Vasilios will be very familiar with, and Payman will be very familiar with, and Jason will be very, very familiar with, and hopefully the rest of you will get very familiar with as well, you typically vary the amount of context set out of the data. Right? So when you define a task, you change the amount of context and you change the amount of target. So you have maybe 1 context point or like 5 context points and 15 target points, and you have 5 target points and 15 context points. So this amortized inference artifact, Q, has to learn how to deal with all different sizes of data sets. Okay.
So like being able to have different sizes for the context and the target, it's a requirement to have like nice posterior, or?
It's subtle, it's required, it seems to be required in order to get the inference artifact to generalize over context set sizes that were not seen during training.
Okay, and when you vary the size of the context and the target, like are you expected to get the same posterior?
Do you mean it when you vary? So if you take a Q
the size,
and you give it more data?
I mean, like we're trying to approximate, like we try to find y of t, right? Given like whatever other things we have observed.
Correct.
So like how will our estimate change if we change like the context and the test size, like the target size?
This is a brilliant question. Thank you for this, right? So dropping all the context, all the stuff for a second. I think the best place to look at this is to look right here, right? So what's going to happen is that when we do posterior predictive inference, right? So the only things we have are this term and this term, right? And we're going to replace this term with this term. But we can think about it in general, what's going to happen anyway. So P of y t given z, so P of y t given x t context theta, right, is equal to da 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 P of y t given z x t theta. And I'm just going to write Q here because that's actually what we're going to do at the end of the day. Okay, so the question is, what happens when we get more data here. Okay. So if this were P, if we have more context data in the graphical model, right? In the graphical model, I'm not gonna. I'll write it again here, right? Just to to remind you, right? This is the context and this is the target. In this graphical model, particularly when you factorize the joint in this way, right? What will happen as the context set grows is that the posterior distribution over Z, given the context distribution, will decrease in entropy. It will become more sharply peaked. Just like Bernstein-von Mises says, eventually, as this gets very, very large, the posterior distribution over Z should contract to a point estimate. We have a parametric model, right? So as the context set gets larger, either Q or P, whichever one we use, should contract in the Bernstein-von Mises sense of contracting towards a point estimate, right? If it contracts to a point estimate, then this is just a regress. It's just a straight regressor, right? Whatever the likelihood that you learn is under theta here, you have the likelihood model for the target values, right? That's all you have. If you have uncertainty about Z, then you have uncertainty about model parameters. This is like a Bayesian neural net kind of thing that's happening as well. So you not only have, you know, whatever likelihood you've learned here, but you also have uncertainty about internal parameters of this thing. So in effect, what happens is that as the context set increases in size, you would expect your posterior predictive to become more sharply peaked. Sharper is the word you're looking for, right? So this is a lovely question. Oh my goodness. Oh, we're totally screwed. Yeah. So let me just say a couple words before we get into sort of architectural details for neural processes. And let's review a couple of concepts, right? A set function is a function that takes an input of a set of objects. Just to foreshadow, all of the context here, this is a set. It's a set of input-output pairs, right? So we have to embed this set somehow, right? So a set function is a function that takes a set, right, and maps to some domain, right? The two important characteristics of sets, they vary in size and they have no order. The question is, how can you implement a neural network set function? We can't feed an orderless set to a neural network. They operate on some sort of ordered list of vectors. Therefore, really what the question is, how can you implement a neural network that operates on list of objects, can absorb an arbitrary size list, and is invariant to the permutation of the list, i.e. for any permutation of its inputs, the function value remains the same. Okay. Just again, to be clear, right, what we're really talking about is we need some sort of distribution object for Z that is permutation invariant with respect to its whatever it's fed, the data input-output pairs it's fed, right? Okay. It turns out that you can look this up, that a function is permutation invariant only if and only if it can be decomposed in the following way. So if f of some set can be decomposed into some outer function rho operating on the sum, in the sum operation, there's a little bit of there's some degree of freedom here. Basically, the summation operator can be replaced with any other permutation invariant operator known as a pooling operator, max, mean, min, so on and so forth. So long as you have some function h, again, can be a neural network, operates on each of the data points individually, and then you do a permutation invariant operator like, again, max, min, mean, so on and so forth. And then some outer thing. Okay. So again, these H's in this row, they can be arbitrarily complex neural networks, but if you want the embedding of your context set in this particular context, in what we're talking about here, to be permutation invariant, then basically you know that the architecture has to look like this. Okay, so this is, again, what we're going to use for permutation invariant pooling operation. Okay. So in the meta learning setup, the set functions come into play when designing architectures for QZ given context. Since the context set in the problem setup in the graphical model is not ordered, the underlying functions representing the posterior to encode the context set are set functions where the input set is the context set of input-output pairs. You could think about doing this with an RNN instead, right? But in order to achieve permutation invariance with an RNN, then you have to use data augmentation. In particular, you have to do basically a factorial amount of data augmentation in order to get the thing to learn a permutation invariant function, which you don't want to do. Okay. So this is the permutation invariant architecture that you should use for Q. A natural thing that you might try would be to use some sort of autoregressive architecture, and that would be a disaster, basically. So neural process models of the sort that we've been just talking about for meta learning, which is like the main topic of today, consist of an encoder-decoder architecture where the encoder implements, not terribly surprisingly, the variational distribution, which takes a context set or really any set of input-output pairs, right? And the decoder implements this likelihood function given theta, right? So the encoder takes input observations from an exchangeable model, and therefore, in order to be efficiently learnable, it has to use an permutation invariant in encoding. So a typical choice in a neural process is to take your input-output pairs, run them through some neural network that gives you some statistic, SI. You do some permutation invariant pooling operation to give you a set encoding. That set encoding is passed through some network rho, and it gives you some parameters for your variational distribution over some variable z. And this variable z, for various reasons, might as well be reparameterizable. It might as well be Gaussian, so most of the time we'll choose this to be a normal distribution, but you know that this would be reparameterized in all of the gradients we would take anyway. Okay. Fine. The decoder is designed basically based on the assumption that the data generating conditional likelihood factorizes. So according to the graphical model, basically, if you're given the latent variable value z and this model parameter theta, then every output given every input is conditionally independent. And now we can just write this down as whatever neural network we want. There are a ton of variants of neural processes that have been proposed. Lots of empirical studies have been done. Conditional neural processes drop the latent variable z. Basically, they make it Dirac distributed, which means that you can just define this thing as a parametric distribution and estimate it directly via negative log likelihood loss. Payman is familiar with this variant, although there's some question about whether or not doing that with z makes any sense in that context, which I would say it doesn't. So anyway, the overall neural process architecture looks like this. This is Q, this is P in the variational autoencoder sense, right? So here is some set of data. We pass it through these H functions, a permutation invariant operator rho, then we get a variational proposal for Z. The decoder takes that value Z, each of the inputs, runs them through some neural network G, and produces an output for each input conditionally independent given the value of Z and, of course, theta. So if you remember theta from the model, theta shows up here. It's the thing that knows how to generate outputs given inputs and a latent variable, right? So this can be an extremely powerful regressor. Okay. I know I've skipped over our break, so I think I'll skip the meta learning, the inference compilation version of this. So there happens to be you could, instead of doing variational inference, you can do an inference compilation version of this as well. But let me give you an example of what this thing or this kind of idea is used for. and what meta learning can do. So here's a 1D regression example. So each plot shows a single test task. Okay, so the task is to infer the output values yt along a fine discretization of the input space. So there's going to be a bunch of xt's along here, right? And this is trained under some data generating process that we know the parameters for, right? And this is just a pedagogical example, right? So the true task input output relationship is shown as a black line for that particular task. So we have a generative model for tasks, and for this particular task, the true input output relationship is this black line here. Okay? We don't know it. All we get is a context set. The context set is that point right there in this particular example. So this is the context set. And using the variational inference procedure, the variational inference procedure needs to produce a posterior distribution over Z. That Z then is used within a generative model to produce for a target X, xt, a distribution over yt, I. And there's a bunch of x's along the horizontal axis, and the y's are again, conditionally independent, blah, 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 right? Okay. So here again, so basically you can see what's happening up here is the context set is of size 1. Right? Here, the context set is of size 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Context set is of size 10. And you can see that however this neural process is learning this thing, this relates to Ina's question, the uncertainty about Z, which characterizes the regression relationship, is smaller, right? The variance of the functions that come out is smaller, as you would expect under being exposed to more data, right? And as the number of context points increases, again, your uncertainty about the function itself decreases in variance. Okay.
Can I ask a question here?
Yeah, please.
Can you maybe point out in this particular pedagogical example, like so I can see what the context is, I can see what the target set is, but like what is the data set? Like, is that a valid question to ask here?
It's totally a valid question. So how would you construct? So this is again a pedagogical example, right? So there's like the metadata set, right? So how would you construct a metadata set for this, right? One way you would construct it the way you would construct this is to do this via a Gaussian process here, right? So I don't want to go through how to do this, but roughly, like story time, you would sample a function from a prior over functions. And then sample a whole bunch of x's from, so this is like f task, and then x tau, xd I would be from some prior on x, and y di would be from some prior on y.
Sorry, wait, yd is not generated by the function on x?
Yeah, sorry. Yes, thank you. Okay. The prior on y being f of x.
Yes, yes.
Plus some noise.
Yeah. Yeah, okay.
So this really is a Gaussian process example, and this is where it comes from. Like you generate, but the basic story there is you generate a function, and a Gaussian process is you just integrate out the function, and you just generate sequentially from some Gaussian with a known covariance structure, right? So that gives you a set of xd, yd, right? And then you partition those into context and target sets as you wish.
Mm-hmm.
and you learn the neural process objective as you go.
Yeah, okay, and here we're just seeing a few examples for a particular pick of context set and target set, right? Like that's
After you've trained theta,
yeah,
which says something about how these things are generated in general, and after you've learned phi, which tells you how to embed the context set such that, you know, blah, 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 these are posterior predictive, draws from the posterior predictive distribution over all of these target inputs. So the context set is very small in this context, and then the number of target inputs is very large, and the number of target outputs is very large. And you can see the target outputs on each of the, you know, they're basically the Y locations. Okay. So this is, if you think about what's going on here, this is pretty cool, right? I can do like non-parametric regression in a hurry. I have a prior over functions, and now I can just like put in a couple of context points, and I get a regression function out very rapidly for free that I can evaluate it at any new input. If you think about, for instance, MNIST digits in this way, you can think about an MNIST digit as being, I'm sorry, I have to use XY again, but you can think about them as being, or basically, maybe I should just do IJ, pixel locations, and the corresponding grayscale value, or in the case of color images, a 3-vector, right? So a vector field instead of a scalar field. Okay? So if you you basically can think of an image as being a 2D function, which maps from pixel locations to their color. If you take this perspective, you can do some pretty ridiculous things with these meta-learning artifacts. Right? So it's worth paying attention to what's going on here. I'll try to zoom in so you can see what's happening. Right? I don't remember which one is which. Yeah, let's just go over here. So what's happening here is there is some trained model for generating images, and there's some trained model for generating pixel values at pixel locations, right? And there is an amortized inference artifact that can take some sort of contextual information and tell you what the distribution over things to draw should be. So the context information, if you look very carefully there, that's quite large, is that you have some pixel values, 1 pixel value, 2 pixel values, 3 pixel values, so on and so forth, up to 30 pixel values. And I guess the question is, you know, what is that? What is the image at 90 pixels or 150 pixels or 300 pixels? So the blue locations are target locations. And the sampled images here, now I don't know why, there we go. The sampled images are posterior predictive samples of Y given X and Z, where Z is the encoding from the amortized inference artifact Q phi given the context pixel values, exactly as described. And what you see per row are samples of this posterior predictive distribution. And again, to Ina's point, as you get more and more contextual information, basically as you get more contextual information, the concentration of posterior predictive mass starts to move towards plausible completions. It tightens, right? So you can see there's actual variability about what the number is. right? But as you move in this direction, it becomes more and more clear, particularly it becomes clear at this point that it's a 2, and now the model learns as will generate 2s. Right? So this is the same thing, but with faces, also kind of remarkable that it can do this, right? So again, the context pixels are given here. And these are samples from the posterior predictive distribution over filling in the rest of this with samples drawn from the model conditioned on this particular context. And as you get more and more and more pixels, this becomes more and more concentrated on particular samples in painting.
Can I also ask like a quick question?
Yes, please. Yeah.
So what's going to happen if you have noise in like the context you're giving to the model? Like how will that affect the predictions?
The noise is accounted for in the graphical model. So if you have noise in the inputs, you're in trouble because we're not modeling the inputs. But if you have noise in the outputs, that's totally fine, right? Because the graphical model has a likelihood function that you've learned, right? It's a good question, made me think. Last example. So, this is a fun one. So here's the ground truth image. We don't show the angles, but you can basically see the angles anyway. This is the context set growing in this way. So here, over a very, very large set of possible models, what happens is we learn a model that goes from a context set and attempts to fill in a target set which consists only of a particular description of one viewpoint. So the entire input is just an angle. So the input is angle, the output is image. The context set is angle 1, noisy image 1. So this actually directly addresses your noise issue. You know, angle 2, image 2, angle 3, image 3, angle 4, image 4. So this basically is the posterior predictive, a sample from the posterior predictive under a neural process learned in the context, learned to do posterior predictive inference in a growing context where the context consists of, again, angle, image, angle, image, angle, image, angle, image, input, output, and then the target is simply one new angle, which is the angle that produces this viewpoint. And you can see as you get more and more views of a particular object, the context set increases, the posterior predictive distribution over what that object looks like from the new view collapses. Right? And you can see these examples all over the place here. Right? Now, I think that's it. I would encourage you to think about the relationship to Prob Prog. And maybe even more to the point, I would encourage you to think about, we've done a bunch of horribly difficult, you know, like algebraic, variational inference, bounds, reparameterization, blah, 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 with little to no reward up to this point, right? Right? The point of all of this is to get you to think about things such that you can engage with this kind of activity, which requires you to think about amortized inference. It requires you to think about model learning. It requires in models with latent variables. It requires you to think about very, very complex graphical models in which you're doing all of this stuff simultaneously, right? So if you actually look at what's happening in these figures, it's really amazingly stupid, and it's very, very close to the kind of amazing stuff that's happening with GPT-3 and that sort of thing. Like, what is this model learning? What is, you know, P of y given x, theta and z, doing here, right? This theta and this model is learning how to draw arbitrary objects from arbitrary perspectives, right? So the model learning stuff we've been talking about is not, you know, like the homework problem kind of model learning things that we've been looking at, but it's really setting us up for being able to deal with and engage with this kind of literature, right? Where the model that you're learning is some deep network's parameters, right? That takes in and consumes randomness in a way that actually matters, right? Like, what is this thing from some other perspective? We don't know. If you look at multiple samples of this, you'll see that it sometimes draws holes, sometimes doesn't draw holes. Like, who knows, right? There's a whole bunch of ambiguity that actually shows up here, right? And it's important to be able to deal with that. That's it for today. I'll just say, you know, amortized inference and prob progs with IID observations is the same thing as meta learning, right? It's exactly the same thing. And if you want to do efficient nesting of prob prog, which we haven't talked about at all, but it's, you know, an advanced topic that's in the book, it requires generalizing over outer environments context, which requires amortized inference, which requires being able to deal with contexts of varying sizes, which requires permutation and variant in embeddings and set functions and all the stuff that we've been talking about here. So there are lots of project ideas that come out of this. There's, you know, there's some on the list that I talked about, and there's a bunch of people in the class who've worked on this sort of stuff. I know they have. Yeah, you can either work on meta learning for prob prog, or you can work on meta learning writ large and tackle some of the problems in meta learning. And what you'll find is that when you work on those problems, the techniques that we've been talking about in class are extremely relevant. So that's it, and I'll take questions. Thank you for letting me abuse the time a little bit today. I appreciate it.
Can I ask a question about the name of neural processes? Is it just the fact that you're effectively sort of generating like the generative process is kind of generating neural networks? Does that make sense? Like, for every Z there is a neural net?
Yeah. I wouldn't put too much faith in that particular name sticking for very long. I think it's a local inflection point in just amortized inference, right? As far as I can tell, like, all neural processes really refers to, and the only thing that you should really maybe think about is the thing that Ina choked on just a little bit, which is the fact that this thing is not P. Like, that's it. Neural processes are just amortized inference, right? That's really all that's going on, except that they use this trick where they replace, they do they do the sequential posterior update and then make this replacement here. As it turns out, it's not strictly speaking necessary to do that, but for whatever reason, it actually generally gives better generalization performance, which is weird. So, I mean, neural processes, you know, the people who work on this have backgrounds in Gaussian processes, and you know.
Okay, clear.
If the context set is like big enough, can you like just cross this out? Like in the formula in 5? I don't know what that's gonna do, but.
So if the context set is big enough, then you can assume that, so if the context set is big enough, then you can assume that a couple of things happen. One is that if the context set is big enough, then you can assume that this thing is approximately equal to this thing because the context set is going to be enormous and swamp the total data set. And if you assume that this thing is Dirac on some value of z, Dirac z star, right? Then the integral, right? So then the posterior predictive distribution, which requires integrating over z, yt, given, so this integral of z x t theta d, we'll just put p of z given c theta dz as the posterior predictive. Well, then if this is Dirac, then this integral collapses to just p, there's no space. Let me write it over here. This just integral collapses to p of y target given, now I'm going to write z star, but I'm going to conveniently write this as Dirac as some function of the context, right? Yt theta, okay? So if this thing has some parameters, then this is now just maximum likelihood. Like literally all you do, and this is what, like, for instance, Payment had worked on. I think he's taken off, but like this is what one version of this story where you say, screw it. We don't want to do all this variational inference. We don't want to deal with the random variables. We don't want to do anything like this. We really just want to say, okay, let's build a meta learning objective and train it in exactly the way that we're talking about here, right? Make a context set, make a target set, learn how to maximize this thing given whatever splits, and then at test time, just plug in whatever you have here. And that works exceedingly well for image classification and that sort of thing. So if you've heard of CNAPs or simple CNAPs or stuff that came out of the group, that's exactly what happens. They just assume that they inappropriately assume that the distribution over Z is Dirac given the context, which literally no way that can be true, but it works very, very well.
Okay, thank you. And I still have like a question about the noise thing. So
Great.
like in the pictures you showed, it looked like the noise is kind of like Gaussian. What's going to happen if you have like different type of noise in different images? Like how will that be modeled in?
So
like
if we if we go back to these, it's really very interesting, right? So yes, you're right, but let's be very careful that this is not sort of like a field of experts or some other kind of image prior thing, if you're familiar with those, right? What's happening here is that each individual pixel gets its own noise, where like this is really is saying that the pixels are conditionally IID, right? So what we know from, say, for instance, very powerful variational autoencoders is that the noise model doesn't matter nearly as much as the architecture does. So basically, if you make the variational architecture sufficiently powerful, then you can get extremely high quality low noise samples. In other words, you can basically learn the noise per pixel to like basically you can make a Gaussian distribution where the variance that you have is just insanely small, right? And it will look okay. I'm scared of doing this because, who knows what I've searched for, but let me look at this really quickly. So as a spin-off of the kind of work we're talking about right now, very explicitly, this will take a little while to load because it's a massively huge PDF. There we go. So this is amortized variational inference meta-learning in a pre-trained model, which is important. But this is the kind of quality that one can extract from these kinds of models. So I would argue that the per pixel noise here is really much less of an issue than is other modeling considerations.
Looks interesting.
It is interesting, yes. More questions, comments? Thank you, Emma. Nice to see you. Hopefully your eyes don't hurt. Yeah.
Thanks.
Can I ask a question?
Please.
So when we're making the context target sets, I've seen a bunch of different ways they split the whole task into the two sets. For example, with image and painting, you can randomly drop pixels like in the picture right now, or just as in the picture you showed us, you can just cover like 3/4 of the images and get the model to infer the rest, right?
Yep.
Is there like any noticeable difference that these different hiding regimes have on the modeling power and so on?
Yeah, I think what you're really saying is how far outside of the defined task can you possibly hope to generalize?
Yeah, exactly. Yeah.
Right. And at least in the work that you're looking at right here, I don't know if we actually put the figures in the paper or not. Let me see really quickly. Maybe it's in the. Yeah. So we trained on only square subregions, and then gave it these relatively uncomfortable, sorry, Naomi, relatively uncomfortable image crops, and yeah, you could. It's doing something. Well, I'll put it that way. That's what I'll say. So I like. It seems to generalize a little bit, but beyond. So there is clearly, and we're probably one NeurIPS cycle behind on this, but there is clearly a project idea here, or set of project ideas that are available on doing hierarchical meta learning, right? Where you do hierarchies of tasks, where tasks are defined in various different ways, and you try to amortize over the task as well. Like this is straight up a reasonable small step forward. We don't know is the short answer. It seems to be some generalization, but I think we could do better. I think I've almost got you on this. Almost. Even Naomi is like paying attention here a little bit. Like this is, you have not been subject to the full set of. It turns out that the model that we build on very specifically, and there's one bit of cherry picking that we did, but you can see it in the results. Yeah, so this will give you even worse nightmares. So it turns out that the pre-trained generative model does not account for facial symmetry. Like, it's very, very bad at representing like bilateral or lateral symmetry, which means that if you look very carefully, or like you know, I'll try to do this right here. Like, if you line those images up on the left-hand side there, those are amazing half faces, totally ridiculously, stupidly amazing. And if I take the same face, I can't drag them over to the other side, unfortunately. But if you take the same faces and only look at the left half, amazing left half faces, but somehow they're not coherent together. And honestly, you know, in many of these circumstances, it would be a little bit disturbing to, you know, find yourself on a Tinder date with somebody with these particular characteristics. Anyway, more questions, comments, criticisms? Everybody's tired? Okay, thank you very much.